Let's solve an integral problem that is actually given or presented from an anime called My Hero Academia. The source of this picture is in the reference, and don't worry, I'm going to post it in the description. Now, yeah, let's go back. How are we going to solve this given integral problem from an anime? So let's have it here. If you're going to observe, this looks complicated. We have e raised to x, e raised to negative x. That's the same thing goes on to the right, and then we have a denominator of 2, yeah. And the thing here is that each of the parentheses, they have their own exponent. One is a cube, one is an 11, you know? So yeah, you can say it is complicated. And not to mention, even the limit, one of the limits, I mean, is complicated, like this, log of 1 plus square root of 2. So is there like a way for us to do this in a simple way? All right. Like how can we get the integral in simple way? Well, there's one, and that is through manipulation. In other words, we have to change the function in which we can solve them easily as much as possible. So how? Let's start first with this two, right? Inside the parentheses, right? We have e raised to x minus e raised to negative x. Wait. Right, e raised to negative x all over 2. This is just the same as hyperbolic sine of x. Hyperbolic sine of x. All right? This is according to a property of a hyperbolic trigonometric function. Right? And on the other hand, e raised to x plus e raised to negative x all over 2. This is just the same as hyperbolic cosine of x. All right? So with that, we can interchange these exponential expression into its hyperbolic trigonometric function. So let me rewrite this. So this e raised to x minus e raised to negative x all over 2, this is hyperbolic sine cube of x. Then here, for e raised to x plus e raised to negative x all over 2, this would become hyperbolic cosine of x raised to 11. That's it. Then let's just copy the other limits. All right. Now, speaking of limits, we can manipulate this upper limit into something better or simpler, in other words. Like, instead of this, like log of 1 plus square root of 2, um, we can do something about that, you know. So what would it be? So here we're going to relate another hyperbolic trigonometric property where the inverse of hyperbolic sine of x is just simply the same as ln of x. Let me change this. Right, ln of x plus the square root of x squared plus 1. Right, that's it. Or instead of ln or natural logarithm like this, we can use common logarithm instead, which is log. All right, log of x plus square root of x squared plus 1. That's it. All right. Okay, so now why did I bring this up? You see, log of x plus square root of x squared plus 1 looks similar to this. They are very similar, you know, because take a look. We have, yeah, 1 plus then square root of 2, right? Look at this one. We have a variable, then plus, then square root. And of course, by function, they both use common logarithm, common logarithmic function. So my point is that is there like a way where we can make this log of x plus square root of x squared plus 1 into this? Is there a way? Well, yes, there is a way. All right. So first, let me copy this one first. All right. Let me just copy uh the fact that inverse hyperbolic sine is the same as log of x plus square root of x squared plus 1. Okay. Now, here's the thing. What I can do here is that I can substitute x as 1. Like, let's say our x is 1. So what happens is that, of course, on the left, we will have inverse hyperbolic sine of 1. And here we will have log of 1 plus square root of 1 squared plus 1. So this is basically log of 1 plus square root of 2. See, now take a look. This is now the same as this one. If you would notice, they're just the same. Now, let's go back again to the equation. Log of 1 plus square root of 2, right? Now, this is the same as inverse hyperbolic sine of 1. So therefore, we can change log of 1 plus square root of 2 into inverse hyperbolic sine of 1. So we can change it into that way. And trust me, it's much better. Later we're going to get the integral out of this, all right? I'm going to explain it later why. Okay, that's it. All right. Now let's go back to the function. Okay, we have this one. So, how are we going to get the integral out of it? So we're going to apply a technique which is a technique for the powers of sine and cosine. Basically, if I have like uh a sine, then it has a given exponent and a cosine that has also an exponent given. Now, how are we going to get the integral? We have a sine, cosine, stick together, and each of them has their own exponent, whether they are the same or not, right? But usually they're different. So what are we going to do? So here, in solving this type of problem, is the same as how we are going to solve this problem, right? Because it has sine and cosine, despite the fact that they are hyperbolic type. So how are we going to solve them? So here's how. There are three conditions. Right? There are three conditions. Like one of them is that what if here your sine function is even, but the exponent of the cosine is odd? Two condition or second condition is what if the exponent of sine is odd, but the exponent of cosine is even. Basically, it's the opposite of the first condition. Now, for the third condition, what if your n and your m are both, or basically, what if the exponent of sine and cosine are both even or odd? All right. Now, if you're going to take a look at this given function, we have cube of sine and 11. You see, both of them are odd. Okay. So we're going to use the third condition here. Okay. Both of them are odd. So we're going to use the third condition. Now, what of it if you're going to use the third condition? Okay, like, okay, it's a third condition. So what are we going to do if that's the case? Let me erase this one. If in the third condition, we are going to use it, then here's what we're going to do. Either we, number one, we will get a factor of hyperbolic sine, or two, we will get a factor of hyperbolic cosine. Either of the two. So if you pick the first choice, what will happen here is that this cube of hyperbolic sine, this would become the square of hyperbolic sine times hyperbolic sine. And there, you get the factor of hyperbolic sine. But if you pick the second choice, which is a factor of hyperbolic cosine, what happens here, this would become hyperbolic cosine of x raised to 10 times hyperbolic cosine of x. So therefore, you get already the factor of hyperbolic cosine. Now, the question is which one? So as I said, you have two choices. So either pick one of them. All right? So for me, I'm going to pick the second one. I'm going to get the factor of hyperbolic cosine. That is what I'm going to do. So okay, now that I did that, what will happen? Okay, as all since we are going to factor a hyperbolic cosine, so here's what will happen. So this would become cosine, a hyperbolic cosine of x raised to 10 times hyperbolic cosine of x. So this is what will be the result. All right? Okay, so now we have this. So what are we going to do? Since you picked the second choice, this is the next step. You see this one. Since this hyperbolic cosine is it has an even exponent, what we're going to do here is that we are going to get the exponent of 2 out of it. In other words, since we have hyperbolic cosine of x raised to 10, instead we can rewrite this as hyperbolic cosine squared of x raised to 5. Basically, we will get a factor of 2 in exponent. All right? Now, if you're asking me why, I'll explain later. Okay, but that's the next step if you're going to pick the second choice. Okay, so we have this now. Let me just copy the other terms here. Wait. No. So yeah, we have the square of hyperbolic cosine of x raised to 5. Then we have hyperbolic cosine x. Okay. Now this, what we're going to do is we're going to apply a Pythagorean identity of a hyperbolic trigonometric function. Okay? Because here in a Pythagorean identity of a hyperbolic trigonometric function, we have the square of hyperbolic cosine of x minus the square of hyperbolic sine of x is equal to 1. Okay? The difference between these two will give you exactly 1. Now, let's just say you want to find the square of hyperbolic cosine. So what we're going to do is we're going to transpose this to the right, and we will have hyperbolic, uh, the square of hyperbolic cosine of x as 1 plus hyperbolic, uh, the square of hyperbolic sine of x. All right? So in other words, we can simply interchange this, the square of hyperbolic sine, into this 1 plus the square of hyperbolic sine of x. So yeah, that's what we're going to do. We're going to interchange it as 1 plus the square of hyperbolic sine of x. All right, so let me just copy the other functions. And here, this would become 1 plus the square of hyperbolic sine of x raised to 5. And yeah, that's it. Okay, now that we have this, what is the next step? Now here, the second step is we will do U substitution. Since you pick the second choice, which is find the factor of hyperbolic cosine of x, then the next step is you did this. Now we will apply U substitution. Okay? An algebraic substitution basically. We're going to let U as hyperbolic sine. Okay? Let U as hyperbolic sine. Then next, what we're going to do here is we're going to get the derivative of hyperbolic sine of x. Recall that if you're going to get the derivative of hyperbolic sine of x, this is just the same as hyperbolic cosine of x. Alright? So this is just simply as hyperbolic cosine of x. That's it. Now, what we're going to do is we will find dx in this equation. Let's find dx in this equation. So what I can do here is I'll cross multiply. I'll multiply them, cross multiply basically. So we will have du as hyperbolic cosine of x times dx. Then, to find dx, what we're going to do is we're going to divide both sides by hyperbolic cosine. So what's left is I have du all over hyperbolic cosine is equal to dx. And that's it. We have found our dx, which is this one. Okay, so now that you have found your u and your dx, we will substitute it in this given function. So we have u as a hyperbolic sign, so we will have u cubed times quantity 1 plus u squared raised to 5 times hyperbolic cosine of x times dx. Your dx here is du all over hyperbolic cosine of x. Oh, whoa, whoa. That's it. And now that we have hyperbolic cosine of x on both sides, here beside it and on below, we can cancel them. So now, wait, by the way, I forgot to put the limits. Wait, I forgot to put the limits. Yeah, so because of that, wait, let me just rearrange this. Oh yeah, so yeah, going back, so because of that, we will have a function as u cubed plus u squared raised to 5. That's it. All right, and let's copy the limits. Okay, now what? Now we can get the integral. Okay. By the way, when you use u substitution, make sure that the variables are all the same. U, U, and then here we have du. If every variable is the same, we're good to go. But if not, well, that means either you use it in the wrong way or algebraic substitution or U substitution rather is not suitable in this problem. Okay? So anyway, you have this. So what are we going to do now? You may be thinking we can now get the integral. Not yet actually. Not yet. You know why? We need to expand these. What I mean by expand, meaning there shall never be parentheses. We have to expand them. We have to uh like for example, I have this one, x plus 1 squared. You see this? This is in factored form, not expand. So you have to expand this. So by expansion, we will have x squared plus 2x plus 1. See, this is expanded. Another example, you see this x times quantity x plus 3. This is in factored form. So you have to expand them. So this would become x squared plus 3x. All right? So you see this? We have to expand them. But here's the problem. You see, we have 1 plus u squared raised to 5. So how are we going to expand them? Well, you have to expand them manually. We have no choice, but we have to expand them manually. And after we expand this fifth, 1 plus u squared to the fifth power, we're going to distribute u cubed to its expanded form. All right? So let's go direct to the point. Like, let's just get the expanded form of, what do you call this one? Of 1 plus u squared to the fifth power. So the expanded form here would be, uh, this would be, wait. This would become, we will have, let me interchange the position of u squared and plus 1. We can do that. Okay. Interchange u squared and plus 1. 1 plus u squared or u squared plus 1, they're just the same. But let me interchange them. So here, this would become, if I'm going to expand them, this would be u squared raised to 5 plus 5 times u squared raised to 4 times 1 raised to 1 plus 10 raised to u squared raised to 3 times 1 raised to 2 plus 10 times u squared raised to 2 times 1 raised to 3 plus 5 times u squared raised to 1 times 1 raised to 4, and lastly, plus 1 raised to 5. Wow, that's actually long. But yeah, wait, this is 0. So this would become, let me just copy first the limits. This would be u cubed raised to, u cubed times quantity u raised to 10 plus 5u raised to 8 plus 10u raised to 6 plus 10u raised to 4 plus 5u squared plus 1. That's it. All right, 4 times 2, 3 times 2, 2 times 2. That's it. Then we will distribute u cube in this parenthesis. So what we will have here is that we will have u cube times u raised to 10 is u raised to 13 plus 8 plus 3, 8, 9, 10, 11. So 5u raised to 11 plus 10 times u raised to 9 plus 10 times u raised to 7 plus 5 times u raised to 5 plus u cube du. Oh, that's it. All right, that's it. Just making sure 3 plus 10, 13. 3 plus 8, 11. 3 plus 6, 9. 3 plus 4, 7. 3 plus 2, 5. And that's it, u cube. Then with that, we can get the integral of this. So we can apply the power rule of integration. Basically, if we have a variable that has an exponent, and if you're going to get the integral out of it, we will have x raised to n plus 1 all over n plus 1. And make sure that their exponent should not be equal to 1, negative 1, if you're going to use this rule. So with that, we will have u raised to 13 plus 1 all over 13 plus 1 plus 5 times u raised to 11 plus 1 all over 11 plus 1 plus 10 raised to plus 10 times u raised to 9 plus 1 all over 9 plus 1 plus 10 times u. This is gonna take a long solution, right? But yeah, u raised to 7 plus 1 all over 7 plus 1 plus 5 times u raised to 5 plus 1 all over 5 plus 1 plus u raised to 3 plus 1 all over 3 plus 1. It's long, all right? Then remember that we have a limits here, which are upper limit, which is inverse hyperbolic sine of 1, and 0 as your normal limit. So let's simplify this first. Okay, let's simplify this first. So here we will have u raised to 14 all over 14 plus 5u raised to 12 all over 12 plus 10u raised to 10 all over 10. Or we can simplify this because we have 10 on both sides. We can just simply cancel out. So we will have u raised to 10 instead. Okay, we will have u raised to 10. Wait. There you go. U raised to 10. Plus here, we will have 10 times u raised to 8 all over 8. But remember, 10 and 8 are both divisible by 2. So 10 divided by 2 is 5. And 8 divided by 2 is 4. So 5 all over 4. All right. Then plus, here we have 5u raised to 6 all over 6. And lastly, u raised to 4 all over 4. That's it. Now we can bring back our u because remember that our u is hyperbolic sine of x. So with that, we will have this one as a result. So we will have 1 all over 14 times hyperbolic sine of x raised to 14. All right. The reason why I bring down the function beside the fraction instead of putting up is because to avoid complicated fraction. Like I don't want to look my fractions complicated. So just simply put it down. All right? Okay, so plus here we have 5 all over 12 times hyperbolic sine of x raised to 12 plus hyperbolic sine of x raised to 10. And I don't want to say the word again. It's too redundant. But yeah, that's it. Okay, that's what we're going to do. Just simply bring back our u as hyperbolic sine of x. Okay. All right. Then lastly, plus 1/4 of hyperbolic sine of 4, hyperbolic sine of x raised to 4. And that's it. All right. Now that we get the integral, but we need to get the value out of it. Okay, we need to get the value of this integral problem because it has limits. But before that, I want to make sure, did I do it correctly? All right, just making sure, right? 13, 11, 9, 7, 5, 3 plus is 5 and cube. Yeah, all of them has plus 3. Okay. Okay, then we get the integral. Okay, good. So with that, we're going to now get the final answer of this by substituting these limits. So first, let's try to substitute. Like what if we have upper limit as inverse of hyperbolic sine of 1? All right, we're going to substitute it in this integral. All right. So what happens here is like this. So here we have 1 all over 14 times hyperbolic sine of h raised to 14 of hyperbolic sine of 1. If you see this one, right, if you see this, all right, this is actually one of the identity of hyperbolic trigonometric function where if you have hyperbolic sine of inverse hyperbolic sine of x, all right, the answer here would be the x. Basically, this would be cancel out. What's left is what's inside of inverse. Basically, what's inside here. So what's inside here is x, right? So that will be the answer. And that's the same thing if we put inverse hyperbolic sine of x first before hyperbolic sine of x. All right. Basically, instead of hyperbolic sine of inverse hyperbolic sine of x, we have inverse hyperbolic sine of x. Wait, inverse hyperbolic sine of hyperbolic sine of x. Still, it's the same thing. We will cancel them. What's left is the x. You see my point? Like whatever, like sine, then inverse sine of x, or inverse sine of x. The answer is still x. So here, you see this one. Wait, let me show you. You see this one? This thing? This is just the same as hyperbolic sine of inverse hyperbolic sine of 1 raised to 14. Okay, we can simply bring out the exponent. And again, we can cancel them. And what's left is we have 1 raised to 14, which is just simply as 1. Therefore, the answer here is 1. That's the answer. 1. And 1 times 1 all over 14 is simply as 1 all over 14. That's it. Right? That's it for the first one. Now, that's the same thing goes on to the other terms, like 5 all over 12, right? 5 all over 12 of hyperbolic sine, okay, raised to 12 of inverse hyperbolic sine of 1. All right. So this one, again, if you would just bring out the exponent here, what happens is that we will have, oh wait, so what happens here is that we will have hyperbolic sine of inverse hyperbolic sine of 1 raised to 12. All right. Then again, simply cancel out the sign and what's left is 1. All right. So we will have 1 raised to 12. and 1 raised to 12 is 1. And 1 times 5 all over 12 is 5 all over 12. That's it. And I think you already know what would be the answer here. All right. So we can safely conclude that if we're going to substitute inverse hyperbolic sign of 1, the answer here, this this hyperbolic sign would be 1. Okay, would be 1. So therefore, we will have this. So we will have 5 all over 12 plus 1 plus 5 all over 4 plus 5 all over 6 plus 1 fourth. That's it, right? That's it. That would be the answer. Okay, when you substitute inverse hyperbolic of 1, right? So wait. 1, 2, 3, 4, 5, 6. Okay, good. Now, we have a lower limit of 0. So we will have minus. Then, we're going to substitute 0 for this. Okay, for this hyperbolic, for this hyperbolic sign function. If you're going to substitute 0 there, the answer would be 0. Okay, if you're going to substitute 0 here in these hyperbolic functions, the answer here would be all 0. Right? Let me check. I could be wrong. Let me check. Let me check. Let me just use my calculator for a second. All right? Hyperbolic sign. For a while, all right? I'm using my calculator here. Wait. Just to show you proof. Yeah, here. This one. Yeah. Hyperbolic of sign, then 0. Yeah, I'm correct. Hyperbolic sign of 0 is simply as 0. That's it. So substitute it here. You will get 1 all over 14 times 0. So you will get 0. Okay, so you will get 0. Then for the second term, 5 all over 12, 0. Sine, hyperbolic sine of x raised to 10, 0. 5 all over 4 times hyperbolic sine of x raised to 8, it's 0. 5 all over 6, 0. 1 fourth, 0. So everything here is 0. So we can just simply disregard them, and we're going to add everything here. Right? So let's add everything here. And I'm too lazy to manually solve them. Let's just use calculator. Right? So here we have 1 all over 14 plus, uh, wait, 1 all over 14 plus 5 all over 12 plus 1 plus 5 all over 4 plus 5 all over 6. And lastly, plus 1 all over 4. All right, so this is the same as, sorry. The value, if we're going to add them, would be 107 all over 28. Am I right? Yes, sir. There we go. All right, that is our answer. Wow, it's actually very long, right? Very long. But at least we get the correct answer. That's all that matters. So yes, 107 all over 28 is the answer for this problem from an anime called My Hero Academia.